Okay, so our next speaker is Nikos from UBITECH. He will present us the blending state-of-the-art open source projects for an early 6G compute and network fabric. So the floor is yours.
Thank you. Okay, so good morning. For those who don't know me, my name is Nikos Psaromanolakis. I'm working for UBITECH the last years. So today I'm going to present to you our work with the title Blending State-of-the-Art Open Source Projects for an Early 6G Compute and Network Fabric. Before we start, let me acknowledge the team that worked behind this talk, Apostolos, Georgios, and Pantelis. So we are tried really hard in order to make this presentation feasible and present this demonstration today. So here we have the agenda. First of all, we're going to start with a small introduction that will discuss about our motivation and the objective, and the relation of this work to the EU Horizon project and to the TFS, of course. Then we're going to dive into the architecture details and interfaces. We're going to present the detailed demonstration workflow. Then we have also prepared for you a video demo, and then of course we're going to conclude this presentation. So just a few words with regards to the motivation. As you already know, the emergence of 6G technologies and infrastructures requires infrastructures that are intelligent, automated, and flexible. And we need to find a way in order to integrate these components and orchestrate them, including the compute and the network resources from diverse domains in an autonomous and in a unique, let's say, way, by providing specific node-bound interfaces and a common, let's say, way for the end users and for the admin users to communicate, let's say, with the controllers. So the 6G requires distributed deployments, especially with regards to the ORAN services, the RU, CU, and DU, since we have an edge continuum, a compute edge continuum that consists of, let's say, far edge compute resources, edge compute resources, cloud compute resources. And there we need also somehow to orchestrate and to manage the transport network in order to create these intercommunications between those resources. So the objective of today's discussion and presentation is to demonstrate a combination of currently state-of-the-art open source projects, namely TeraFlowSDN, OpenSlice, OpenAir Interface, and ORAN-based OSMO, P4 Stratum, and Maestro, and demonstrate that how these open source projects are capable of effectively integrated to build a flexible and programmable and standard, let's say, aligned computer network fabric in order to pave the way for an early 6G infrastructure. So why this work is relevant for our projects? First of all, with regards to the Protect 6G projects, there we have the need to demonstrate an end-to-end ORAN deployment with dynamic functional splits managed by standardized orchestrator ecosystem. And secondly, we need to configure the transport network that consists of optical and packet devices through the TFS controller. And then we have the across projects where there we have the need to employ P4 switches for orchestrating the transport network for ORAN-based 6G infrastructure. So why is this relevant to the TFS? Because with this POC, we managed to contribute in several domains. First of all, we tried to update the northbound interface of the TFS with regards to the ITF network slice model. We have created a middleware translator from the ITF network slice controller and model to P4 switches and configurations to the P4 devices. and we managed to configure the backhaul and midhaul transport networks. I'm going to explain this in the next slides. And last but not least, we have achieved the integration of the TFS controller with a SMO, with an ORAN-based SMO. Here, it is worth mentioning that the focus of this presentation is to showcase the programmability, the control plane testing, and the integration of our transport network, and not to validate, let's say, the performance and the KPIs that we're capable of achieving. Since now we're going to have only P4 switches in the transport network. So let's dive into the architectural details. This is the target, let's say, testbed. As you can see here, the right side of this architecture consists of 3 TeraFlowSDN controllers. We have the end-to-end orchestrator and 2 controllers underneath, the packet and the optical. And the point here is that we need 2 controllers, one for packet, one for opticals, because the transport network, it may consist of optical devices, for example, transponders or something like that, and packet devices. So given that in our testbed, we don't have, in the UBITECH testbed currently, we don't have any optical devices, we simplified this diagram and we keep only 1 TeraFlowSDN controller. We removed, let's say, the optical TeraFlowSDN controller, and the point here is to find a way to orchestrate both the compute resources, but as well the transport switches, the resources that are capable of, let's say, creating the transport network in our case. So what you can see here is that we can say that we have two fabrics. First of all, the final goal, if we can say it like that, is that somehow we need to be able to deploy in our infrastructure a functional split. Here you can see that the functional split is consist of ORU, ODU, and OCU, and we need a way to let's say to create a distributed deployment across the entire edge to cloud infrastructure, and then we need somehow, by utilizing the TeraFlowSDN, to create the connectivity between OCU and ODU, OCU, and the 5G core. So here we can say that the compute fabric, let's say, orchestration plane and control plane is consist of the Maestro, an open source platform, not an open source, but this is a platform that is developed by us, by UBITECH, and our plan is to make it open source by the end of this year. The Open Slice by Etsy, the compute controller, we can simplify it as, let's say, a Kubernetes master node. And all this stuff and all these controllers will be managed to deploy these pods and these ORAN services. Then we have, let's say, the network fabric architecture, where here you can see that we have the TeraFlowSDN controller and the P4 switches underneath. Last but not least, on the upper layer, we have the SMO, and it is pretty obvious that the SMO should orchestrate and manage both the network fabric, and also the compute fabric. So with regards to the TeraFlow architecture and the focus here, I have outlined, let's say, the components that we are going to be utilized from the TeraFlowSDN. These are the northbound interface, the ITF slice, the context, of course, the slice component, the service, the P4 southbound interface, and the path computation. And now we can dive into the demonstration workflow step by step. So if we can call it day 0 and step 0, first we need to provision the TFS controller, and in our case, we are only utilize these 7 components of TeraFlow. So if we manage to install successfully the TeraFlowSDN controller, then we can have, let's say, this frame of the architecture. As you can see, right now, in the initial step of the demo, we don't have almost anything underneath. As you can see, we don't have any pod deployed or any rule, let's say, configured in order to connect the edge to the cloud and to the data network. So first, we have created a static, let's say, intent. In this case, we can call it infrastructure deployment. This request is, let's say, the end user sent this request to SMO. In our case, we are utilizing a Helm chart, but it's called functional split 2. So our goal is to deploy functional split 2 in our infrastructure in the testbed of UBITECH. And we give also a slice ID, which is called orange slice. So how this works? First, the SMO will get this information from the end user. It will dispatch this information to the Maestro. Maestro will ask the open slice in order to provide to it a Kubernetes as a service. The open slice will return the infrastructure, and then the Maestro will be capable of deploying these services. Here, again, it is worth mentioning that the interfaces between SMO, Maestro, and OpenSlice are all based on standardized TMF APIs, the service order, the service vendor, and the service specification. So if the Maestro send this, when the Maestro will send this command to the compute controller, first, what we're going to see is two pods in our, let's say, first node, the ORU and the ODU. And then we're going to have one more pod, the OCU functionality, in our NUC in the middle of this diagram. After that, we need to onboard this topology into the TeraFlowSDN. So if we onboard this topology, we're going to see this diagram in the dashboard of the TeraFlow. So here you can see the antenna, the RU, the ODU, a P4 switch, the OCU, again a P4 switch, and the control and the CM. So after that, it is time to send our second intent. Now it is called network slice intent. Here we are requesting again from the testbed of UBITECH with the metadata around slice, which in our case is exactly the same with the previous intent. So the metadata is exactly the same. So now the SMO is capable of understanding and correlate this request to the previous one in order to make feasible, let's say, in order to configure this transport network. So it dispatches and transforms this request to the IETF network slice model. It dispatches it to the TeraFlowSDN, and the TeraFlowSDN will then create these links. First, it will connect the OCU with the ODU with a mid-haul by configuring the mid-haul, let's say, P4 switch, and then we'll configure the backhaul P4 switch that connects the CU with the 5G core. Since we are here for the ecosystem day of the TFS, here I have created, let's say, a more detailed view of how the TFS is going to work in this case. The SMO will send this to the northbound interface. This information will pass from slice service, path computation, and SBI. And finally, we are able to see that this transport network is created, and we are able to create, let's say, a ping from the antenna to the internet. Okay, if we dive into more details about the IETF network slice model, here is pretty obvious that we know the IP of the P4 switch, so we have used the ISDP list where we have the IP of P4. We know the IPs of the CU and DU and the domains. That's why we have created this match criteria. The SMO will create in an autonomous way this match criteria. And again, here we have the connectivity constructs and 1 and 2, the sender and the receiver ports. So finally, if everything is deployed successfully, we're going to validate it by, let's say, trying to ping the internet and the data network from the emulated UEs that we have. So now I think that is the time to show to you our demo. This one I uploaded previously. No, okay, I see it. Okay, so first we can validate that we have the file. Anyway. Okay, I'm fine. So here we can validate that we have an SMO deployed, and we have also deployed a 5G core in our cloud testbed. So here you can see all the components of the 5G core. Again, it is worth mentioning that we are capable of deploying these 5G core components by the Maestro by utilizing our orchestrator and the OpenSlice again. But this is, let's say, we can say that all these components are now pre-deployed. So first, we're going to start with a request to the SMO with regards to the functional split deployment. Here you can see the JSON object that I presented to you previously. If we execute a send command, a post command, you're going to see that we received that the functional split is deployed. If we go to the Maestro Swagger, just to validate that everything has passed through Maestro, if we go to the service ordering management and to execute their request, you're going to see that the order is in progress. Okay, great. So the order now is in status in progress. Then if we jump to the OpenSlice dashboard, we need to validate again that the information has arrived here. So here you can see the request that the Maestro sent to the OpenSlice. Again, now the OpenSlice is trying to create the Kubernetes as a service. The status here is in progress. If we refresh the page, we're going to have a completed, let's say, status. And if, of course, we go back to the Maestro, then the Maestro, given that it has the cluster, is capable of deploying the functional splits to the underneath infrastructure. So everything now is completed. And now is the time to validate our request. So you can see here the 4 components of the functional split. 2 of them are deployed in our far edge, let's say, node, and 1 of them in our edge node. And if we try to ping the data network, since currently we have not, let's say, configured the transport network, you're going to see that we are unable of interacting with the internet. Of course, given that we have deployed the functional split, the 5G core have provided IPs to all the components, since the P4 switches are involved only in the data plane and not in the control plane. So here, the end user will try to ping the internet. As you can see, this will not end successfully. So it specifies exactly the interface, given that this traffic needs to go from all the components of the RAN and from the 5G core. So as you can see, we're unable of pinging the internet. Then we need to configure our transport network. So here you can validate that we don't have any services, no configured device at all. So if we go back to the SMO, now is the time to send this slice intent. Here again is the same. We have the same JSON as I presented to you previously. We send the command. We receive that the slice is created successfully. And if we go back to the TeraFlow dashboard, you're gonna see that two services are created, one for the backhaul switch and one for the midhaul switch. And now, of course, if we go back to the terminal, we have a successful ping from the end user to the internet. Okay. Here, we also validate that the traffic and the packets has really passed from all the ORAN services and the 5G core that we deployed previously. So we just simply execute some TCP dumps commands here in order to validate this. Let me forward this. Okay, so let me go back to the presentation. So what we demonstrated, we are managing to demonstrate an integrated and operational, let's say, early 6G computed network fabric. The deployment of a working end-to-end functional split with emulated RUs, and we demonstrated how the SMO, the Maestro, the on slice, and the TF, a Kubernetes cluster are capable of deploying these RU, DU, and CU components as a pods. We showcased how the TFS can be involved in this, let's say, workflow by configuring the P4 switches. And with regards to the next steps, we can split them, let's say, into three domains. First of all, with regards to the TeraFlowSDN, we need to expand and test the controller architecture in our testbed to involve also the end-to-end orchestrator, the optical controller, and to add also in the transport network the optical devices that are, let's say, developed within Protect 6G. We need also to involve the automation and the policy components of the TeraFlow in order to create these policy SLOs and to be capable of, let's say, monitor the metrics of our transport network. We need to utilize the newly introduced IETF network slice controller, since currently we only utilize the IETF network slice model of the TFS. And it will be also a great idea to create a database framework for this IETF network slice model. With regards to the SMO, we need to test more functional splits, especially the functional split 7.2. We need to use real USRPs rather than emulated for radio units and real commercial devices. And with regards to Maestro, we are trying to create a workflow that will have a dynamic ORAN functional split as a service with real-time reconfigurations and monitoring of all of these metrics. So that's all from my side. Thank you for your attention. I will be happy to answer your questions. Thank you again. This is good. Thanks.
I'm curious to like the performance of your orchestrator in the sense that once you put they are deployed to the other when you activate it, how long does it take for that?
I would say less than 5 seconds. Yeah. Actually, the problem here is if we utilize an already deployed, let's say, Kubernetes, this will be definitely under 5 seconds. But in case that we are requesting a Kubernetes and the cluster that does not exist, so the OpenSlice needs to create in a dynamic way this new cluster and attach this to the Maestro, this will take almost 1 minute. Bit more.
Depends on the search application.
Okay.
Yeah, I don't know, but a few minutes, something like that.
Thank you. Any other question?
Any other question? Okay.
Thank you.